Welcome to the Snake Bros Kids YouTube channel. Today we are investigating the fascinating processes behind fossil formation. Fossils form when a once living creature's biological material or evidence of the creature's activities undergo a variety of preservation processes. The time capsules created by fossils are valuable for researchers interpreting past life forms and the relationship of events in geologic history. Paleontology is the field of study that utilizes the fossil record to draw conclusions about past life forms. Because already mineralized parts such as bones, shells, and teeth are more easily preserved, most envision the fossil record to be composed of these remains. With advances in technology, paleontologists are recognizing the vast knowledge awaiting in the fossils of tiny microbes as well. Taphonomy is the term used by paleontologists to describe the timeline of events between an organism's death and its preservation as a fossil. Our exploration today will be focused on the taphonomy of the two most visible types of fossils, body fossils and trace fossils. Body fossils are formed from the remains of an organism's body parts. The remains can be altered through the processes of permineralization, replacement, and carbonization. In rare cases, an organism's remains are considered unaltered if they undergo preservation through entombment in amber, ice, or tar. Even as we have an abundance of examples, most organisms do not become fossils. In fact, fossilization involves an unlikely confluence of numerous factors. Upon death, most organisms' constituents are completely cycled back into the environment, leaving no legacy of their existence. A body fossil, however, can be formed under prime preservation conditions. The most important factor affecting preservation is rapid burial in mud, sand, volcanic ash, or other fine particle sediment, thereby cutting off exposure to oxygen and eliminating the possibility of complete decomposition. After burial, any soft tissue will continue to decay, but the denser structures of hard parts will remain, allowing time for organic material to be acted upon by mineral deposits. The sediment around the transforming organic material continues to accumulate and compact, eventually turning to stone all around the remains. Another essential preservation factor is flowing water rich in dissolved minerals. Water acts as a delivery vessel, transporting mineral deposits into the tiny hollow spaces of the slow decaying organic material. In the permineralization process, an internal cast is formed by deposited minerals crystallizing along porous cell walls. Crystals continue to grow on the inner surface of cell walls until the central cavity of a cell is completely filled. This process does not fully replace the organic material though, as cell walls remain intact around the crystals. Silicification is the most common fossilization process. Because of its small molecular size, stable chemistry, and abundance in nature, silica, also known as silicon dioxide, is a master preserver. During silicification, percolating water, supersaturated with the silica minerals, simultaneously dissolves carbonate structures and precipitates the silica that is no longer soluble in the water. Like a reverse 3D printer over the course of thousands of years, silica crystals are deposited in the exact form of the once living organism. Silicification completely replaces organic material, creating a stone copy of the original. Pyritization is another mechanism by which organic material is completely replaced. Pyrite, formerly known as iron sulfide and informally known as fool's gold, can be precipitated out of groundwater as it reacts with sulfides from decaying organic material. An organic carbonate structure, such as a shell that has been replaced by pyrite deposits, is said to be pyritized and can have a striking metallic appearance. Another fossilization process that is well suited for preserving delicate organic material, such as plant tissues, insects, or the bones of fish, is called carbonization. The heat, pressure, and protection from oxidation brought on by rapid burial causes gases and fluids emitted from decomposing organic material to become compressed, resulting in a residual thin film of carbon. Fossils become exposed over millions of years by erosion and geological activity. When they are brought to light for us to discover and study, we are gazing upon the molds and casts of ancient life. A mold is a three-dimensional impression of all or part of a fossil. If that impression fills with new sediment, it creates a cast. Casts are made from molds, and sometimes both molds and casts are preserved, creating a positive and a negative record of an organism. The processes yielding body fossils are just some examples of how molds and casts are made. Trace fossils are also frequently preserved as molds and casts. Trace fossils, otherwise known as ichnofossils, consist of evidence of an organism's activities rather than its physical constituents. Trace fossils include preserved footprints, trackways, burrows, and dens, as well as coprolites and gastroliths. Even the imprint of nests and eggshells can be transformed into trace fossils. Trace fossils form when an organism's activities become impressed upon a surface of soft sediment. Similar to body fossils, a fine particle clay or silica-rich silt lends itself best to preservation. Trace fossils can be grouped based on what type of activity the impression recorded. Bioturbation describes the record of burrows, resting places, tracks, and trails. Footprints are the most recognizable form of bioturbation. Bioerosion describes the erosion of displaced materials as a result of boring, scraping, or biting. In a marine environment, this can be achieved by mollusks, sponges, crustaceans, and numerous other small marine life. On dry land, chemical secretions by pioneer plants or lichens and mechanical forces such as root growth can also be considered bioerosion. Coprolites, or fossilized fecal matter, are of particular interest to paleontologists because of the insight they provide into an organism's diet. Although classified as trace fossils, they undergo the same mineral replacement process as body fossils. Coprolites can retain detailed impressions of food particles, bones, parasites, and other organic remains. In addition, modern scientific techniques are rapidly expanding the knowledge to be gained from these fossilized remains. Gastroliths are small stones swallowed by a bird, reptile, or fish to aid in digestion in the gizzard. A gastrolith becomes rounded on all edges because of it being acted upon by other stones and fibrous material in a process analogous to a rock tumbler. There are many living creatures that utilize gastroliths, but fossilized ones found among sauropod and plesiosaur remains have proved especially valuable in evaluating the dietary habits and migration patterns of these Jurassic and Cretaceous-era dinosaurs. Fossils are some of the most beautiful and informative treasures from Earth's past. Although we now use the scientific method to acquire understanding of fossilization, the process of turning living things into stone could be perceived as nothing short of magic. From the Gorgons of Greek mythology, who were said to petrify anything that met their gaze, to the Celtic tales of dancers and musicians being turned into megalithic standing stones, and to the petrification superpowers imbued to characters of modern fiction and video games, the ability of life to be transformed into stone never ceases to engage human curiosity. What term is used to describe the timeline of events between an organism's death and its preservation as a fossil?
Taxonomy.
What molecule is known as the master preserver and is a common part of fossilization?
Silica.
What type of fossil consists of evidence of an organism's activities rather than its physical parts?
Trace fossils.